Welcome back. We are at lecture 58. Guess we've got some WebAssign problems on the docket for today. I also want to go through the test. I mentioned yesterday that the test 4 grades were not things of beauty. In fact, they were probably, if you can think of the symmetric image of things of beauty on the other side of the planet or solar system, that would be the category that they would fall in. Probably not worthy of television at the 5 o'clock hour, and probably we do not want to put that on videotape for future generations, what the results of that test were. So let's go through some things. Some of the things I am baffled by mistakes that were made. You tell me. That's one of the reasons why I want to go through the test. If you think that problem was particularly unfair, this is the day to voice that opinion. But don't voice it till we're through going through the problem. Okay? I mean, you look at it and you say, that's unfair. Well, let's go through it. And after we go through it, you still think it's unfair, then let me have it. All right, now everybody should have their test and should have a solution set for the test. Were you surprised that this test included integration by parts? No. You were expecting integration by parts. Okay? Problem 1. So there is some memorization there, but I think just by sheer repetition, you probably didn't have to work at it to memorize that. We've used it enough. So if you can put an integral in the form of u and dv, and that takes care of everything, then the integral, it integrates into uv minus the integral of v du. So we're hoping that that is workable and doable, and u dv by itself is not. So this problem is natural log of x over x squared dx. You can say that u is the natural log of x, but what's wrong with saying dv is x squared? Yeah, we don't have an x squared in this integrand. We have a 1 over x squared. So if it helps, and we had done this on an example or two, to kind of break it out into its real pieces, natural log of x is one of the pieces. X squared is not one of the other pieces, because that would be u over dv. We don't have a u over dv. We want a u times dv. So if you're going to let this equal u, then everything else has to be dv. And that works. We let u equal natural log of x and dv equal to 1 over x squared dx. That's everything in the integrand. Derivative of natural log. Antiderivative, because we know dv, we want to find v, so we're anti-differentiating. If it helps, this is x to the negative second, which is not natural log of x squared. X, that only works when it's x to the negative first. So, but we can use that rule by adding 1 to the exponent, dividing by the new exponent. So x to the negative 1 over negative 1. So there were errors here. Had several people pick x squared as dv. We don't have an x squared in the integrand. We have a 1 over x squared. And then several people that anti-differentiated this and got x to the negative third over negative 3. That's not the rule. We add 1 to the exponent, divide by the new exponent. And if it helps, to call that 1 over x. So at this point in the problem, u, v minus the integral of v du. And there's a little repetition here in this problem, because if you want to bring that negative sign out in front, that's a plus. And we've got 1 over x squared dx. Well, we already did that up here, so now we're doing that again. So the antiderivative of x to the negative second is x to the negative first over negative 1. And you can rewrite that, but that's the final solution. Anything about that problem that it was unexpected or unfair? Yes, Alyssa. Okay.
For v, where it's originally x to the negative 1 over negative 1, how did you switch it to get to negative 1 over?
Well, this is dv, this piece of the integrand right here. So 1 over x squared, I just rewrote that as x to the negative second because I was going to use the power rule. So the power rule, we have dv and we want v, we're anti-differentiating. So we're really looking at that. That's how we get v, integrate or anti-differentiate this. So as long as the power is not negative 1, we can add 1 to the power and divide by the new power. You would do that same thing with x squared. You would say x to the 3 over 3. So we add 1 to the power here, x to the negative 1 over negative 1. So if it's worth a few minutes of class time and you see a similar problem on the final exam and you get it corrected, then I guess it's worth it for spending a few moments of class time on this. And I'm not just pointing the finger at you. I realize that when something is missed across the board, not that this problem was missed across the board, but it was missed by several people, apparently I didn't do my job very well either. So is there anything, any question about any part of this or integration by parts? That's a final exam, pretty much guaranteed question. All right. Second question. And I guess there's a WebAssign. We may do this test question and then move to the WebAssign question that's similar while we're on this topic. So if you saw this and you thought to yourself, that's a decomposition into partial fractions. So this is a partial fractions. And I wanted to get a problem that included kind of both cases, but yet wasn't like unbelievably complex with too many variables. So we're going to have an A and a B and a C. And we could do repeated linear factors and repeated quadratic factors, but I opted away from that because of time on the test. It takes too long. First of all, one of the things you might want to consider when you see a problem that looks like it is probably going to be partial fractions is, do I need to divide first? Do I need to do any long division? The numerator is x squared. The denominator is what? X cubed, so we're okay, right? As long as the degree of the numerator is smaller than the degree of the denominator, we just do our little partial fractions thing off to the side. Now, look at problem 7. What's the degree of the numerator? Squared. What's the degree of the denominator? To the 1, what probably should come up in your mind there? I mean, there's no partial fractions anyway. But if the degree of the numerator is larger than the denominator, what do? Divide. You divide first. And I've got another set of comments on that I'll make, and that's probably the one problem I want to diffuse more than any other problem. Pretty much missed across the board. Not very many points at all by anybody on that problem. All right, so we're going to take off to the side. And this is unfortunately one of those problems that if you don't get this step right, just about everything that follows is kind of, it's not very correct, because you've got to decompose it properly to get it into fractions that we can actually integrate. Well, some of you factored this, so I hope that I don't hurt your feelings too badly, but probably in 7th and 8th grade was the first time you had the sum of two things squared, and you said to yourself, doggone it, that doesn't factor. The sum of two squares does not factor. It never has factored, and it never will factor. That's an irreducible quadratic. That's why I put it in the problem, so you wouldn't have to factor it. It's not factorable. We're stuck with an irreducible quadratic. Factoring, when I say factoring, I'm talking about factoring over the reals. You could factor it in terms of imaginaries, but we don't deal in this class with imaginary numbers. All right, linear factor. What kind of numerator does a linear factor get?
A constant.
Constant. We don't know the constant, so we give it a temporary name, A. This is an irreducible quadratic factor. What kind of numerator does it get?
Linear.
Linear. We don't know the nature of the linear factor, but we know it maybe has some x and it maybe has a constant, so there's the initial decomposition. Any question about that? Unfair at this point?
Yeah.
No. All right, so then we get a common denominator. So the one that doesn't have an x plus 3 needs an x plus 3, numerator and denominator. The one that doesn't have an x squared plus 4 needs an x squared plus 4, numerator and denominator. So at this point, the denominators are all equal, right? So we can basically just look at the numerators. What is it that's going to make them? And there were people that got to this point in the problem that still lost a couple points. So let's get it to the point where we have A and B and C, and we still had a few people that got to those values and still lost a couple of points because of one of the integrands. Is that okay with everybody? That the denominators here and the denominator here and the denominator here are all equal, so I'm leaving them out. The numerator would be this numerator plus this numerator all over that common denominator. So, but we're leaving out the denominators. So let's distribute the A and distribute the bx to both of these. What is that? Bx squared plus 3bx. Distribute the c to both of these. Cx 3c. So now we look at like terms, left side and right side of the equal sign. How many x squared do we have over here on the right side?
A plus B.
So that took care of that and that. How many x do we have over here? 3b plus c. And then everything else that doesn't have an x squared or an x is a constant. All right, so what are the three equations that result? Okay, the coefficient of x squared here has to be the same, left side and right side. So 7 equals a plus b. 12 has to equal 3b plus c. And minus 1 has to be 4a plus 3c. Now what would be ideal is that if we had one of the letters already established and we can kind of work our way through, but we're not quite that lucky. This has an a and a b, this has a b and a c, and this has an a and a c. So the easiest one to work with is probably this one. And if you would solve for either A or B, then you can replace it into one of the other equations so we can eliminate the one letter that we don't want. It doesn't really matter that much. If we solve for A, what would we get? 7 minus B. And then in the other equation that has A in it, we'll get rid of A by putting in 7 minus B. So this equation stays the same. It already has a B and a C in it. This one, once we get rid of A, will now also have a B and a C in it. Thank you. So 12 equals 3B plus C. Let's see what we can come up with. We've got a 3C, right? Mm-hmm. Over here, and a what? Minus 4B? Yeah. And then we've also got a 28 over here, which if we move that to the other side, we'd be subtracting 28, so this is what?
29.
So we've got B's and C's in both these equations, but if we just add them up or subtract them, we're not going to knock either one of them out. What can we do to get it so that the C's drop out?
Multiplied by 3.
Top one by 3 or negative 3. So actually negative 3 is a little smoother because then we can add, right? Mm-hmm. So let's take this equation times negative 3, negative 36, negative 9B, minus 3C, and we'll just leave this one alone. Now we can add them. So if we add these, those drop out, and we have what? Negative 13B, and what is their sum? Negative 65. So you can divide both sides by negative 13. B is 5?
Yes, 5.
And then you can work your way back. We have, as soon as we know B, we can take 7 minus B, and we have A. Which is 2. And then for C, I don't know what the easiest equation is. This one, negative 1 equals 4A plus 3C. 4A is 4 2's. So negative 1 is 8 plus 3C. Subtract 8 from both sides. 3C is negative 9. C is negative 3. Is that all right? Now, that's unfortunately not the end of it, but that's probably the hardest part of the problem, is to get to the point where we have A and B and C. So there's B, there's A, and there's C. So now we put those back into the original decomposed partial fraction setup, which was A over x plus 3. What was A? 2. And bx plus c, so that is 5x minus 3 all over this irreducible quadratic. So that's the goal, is to get it in that form. What's the first one? We've done probably 57 of these. Now this one, I would recommend, and we had done 1 or 2 in class, splitting it up into 2 pieces. This one, you can let U equal the denominator. Derivative of u is 2x dx, and this one is going to become a natural log integrand. This one, that's one that I ask you to memorize, the inverse tangent integrand. Inverse tangent of something, right? The 5 is not needed. Slide it out front. We need a 2 up there. Let's manufacture a 2, but we've also got to divide by 2. Now the numerator is 2x dx, which is du. The denominator is x squared plus 4, which is u. It's du over u. What's that? Natural log.
Natural log, yes.
I'll go ahead and put absolute value. It doesn't need to be there because it's positive. Now, this is probably just a memorized thing. This, when you recognize you have a number over x squared plus 4, we had actually done this all the way through. Kind of in the generic version, and we ended up with 1 over a
inverse tangent x over.
So for this problem, we've got a little extra baggage. We've got a 3. We'll just farm that out to the front. And then what? 1 over 2 inverse tangent of x over 2 plus c. Lengthy problem could have been lengthier if we'd had repeated linear factors or repeated quadratic factors. But I don't necessarily think that any piece of it is unfair. This is, I think, maybe caught some of you by surprise, but we had dealt with it on a couple of occasions. Questions on that? Any surprises to you in that problem in any part that you think is unfair? You wouldn't say it anyway, would you? You can tell me after class if you think anything that I ask you in class is unfair and you were just not comfortable saying it in class. And we'll just agree to disagree on that one. All right, so the web assign. There is a partial fractions number 6. Let's at least get it set up. The original problem, I think everybody probably has the same problem here. X squared plus 1. I think I'll factor that. No, let me remember back to middle school, and I remember that that doesn't factor. Okay? Sorry. Couldn't let that go by. Can we go directly to the decomposition? Is the degree of the numerator smaller than the degree of the denominator? Okay, so we don't need to divide. So we only have 2. They don't factor. They're irreducible quadratics. And from the previous problem, when we have an irreducible quadratic in the denominator, what kind of numerator? Linear. And we don't know the nature of the linear factor. So it's so many x plus a number, possibly, and then so many x plus a number. And we don't know that any of those are the same. So we allow, they might be the same. A and B might be the same. A and D might be the same, but they might be different, probably are different. So we'll allow for the possibility of them being different. Any questions on that piece of this problem? What would be the next step? Common denominator. Okay, now the denominators are all the same, so it's a matter of making the numerators the same. All right, so let's multiply it all up. We've got let's run the ax through both of these. That'd be ax cubed. What, 4ax? Run the b through both of those. Bx squared plus 4b. Let's do the same thing over here with cx. Cx cubed and cx. Dx squared and d. All right, so it looks like we've got some x cubed over here. How many x cubed?
0. Oh, well, a plus c.
A plus c. How many x cubed do we have on the left side?
0.
We have 0 of them. So apparently a plus c is going to be 0. How many x squared do we have?
B plus D.
B plus d. How many x do we have?
4a plus c.
And everything else
D.
is a constant. 4b plus d. So what are the equations that result from left side equating like terms?
A plus c equals 0.
Okay, we don't have any cubed on the left side. We have a plus c on the right side.
B plus d equals 2.
Okay, 2 is the coefficient here. B plus d is the coefficient here.
4a plus c equals 0.
Good. We don't have any x over here. So apparently 4a plus c is 0.
And d equals 5.
And then constant here has to be constant here. All right, we do have 4 equations. We do have 4 variables, but I don't think it's the typical or the worst case scenario of 4 equations and 4 variables. What are the recommendations?
Solve for D and the B plus D equals 2.
I'd multiply it by -1.
No, wait. I thought d.
Subtract out the d from
Oh, I forgot the 4b.
b plus d.
What do you notice about these 2 equations? And
I'll have
the first and third have a and c,
So there's no a and c.
right? And the second and fourth have b and d.
Yes.
So, I don't know. Is that going to get us anywhere?
Can you assume that a and c are both 0?
Or they're both the same number.
no.
Well, one is the
can't
negative
do
of
A.
the other, right?
Yeah.
Because
Both
from
of
this
them are
equation,
negative of the other.
a is negative c,
4
right?
times.
Yeah, well, that.
And if a is negative c, then this equation becomes what?
Negative.
Instead of 4 times a, it becomes 4 times
Negative c.
negative c plus c
Equals 0.
equals 0. Negative 4c plus c is 0. Negative 3c is 0. So c is 0.
Oh.
For 4a, since a is negative c,
Oh.
I got rid of a and plugged in negative c. So we end up with negative 3c is 0. So c is 0. And then we negate c to get a. And if c is 0, then a is 0. So a and c are both 0. And then you can somehow put these together. I guess we could write them out and just subtract them, right? B plus d is 2. 4b plus d is 5. Since the coefficient of d is the same, let's just subtract the second from the first. What? Negative 3b. D minus d, they drop out. 2 minus 5 is negative 3, so b is 1. And if b plus d is 2 and b is 1, then d is 1. So let's go back to the original decomposition. There's our first decomposed or partial fraction. There's our second one. So what do we know? A and C are both 0. So 0x plus b, what was b? 1?
1 over x squared.
And cx plus d, c is 0, so 0x plus d. Inverse tangent?
Yes.
Inverse tangent. Okay, you can take it from there.
Wait, would the second one be 1/4 tangent -1 of...
1/2, because a squared, this is our u squared, and this is our a squared. So a would be 2 here, a would be 1 here.
Okay. 1/2 tangent inverse of x over a.
Let's go back to the test, and I'm going to make sure that we get the problems that I wanted to hit today. Let's go on to 7. It is a definite integral. I don't think that's the issue. The limits are 2 and 5. I'll bring those in at the end of the problem. I think the issue is kind of how to start this problem. Now, there are a couple things from algebra that we probably ought to make sure from this day forward in your life that you distinguish between what you can do algebraically and what you cannot do. Here's a situation when you have a sum or difference in the denominator. So let's just take a fraction off to the side. Let's take 3 over 1 plus 2. That's how much money you have in your pocket, which if you have 3 over 1 plus $2, how much do you have?
1.
You have $1 in your pocket. Now, is it legal to say, well, since I have 3 over 1 plus $2 in my pocket, I'm going to say that's 3 over 1 plus 3 over 2.
No.
Boy, that'd be nice. Wouldn't that be nice? The whole monetary system would be in our favor. We could just convert all our money into more money legally. But is 3 over 3, which is equal to 1, is that 3 plus 1.5? I don't think so. I don't think so. Okay, we can't do that. We can't split up the denominator. Now, if we have a numerator that is a sum and difference, so I guess what I'm saying is there were several of you in here that wrote r squared over r, and this actually kind of pains me to write this, plus r squared over 4. Can't do that. We can't do that. If that were legal, then this would be legal, and we'd be in a mess. So that clearly, you can't do that. You can't split up a sum and difference in the denominator. If that sum and difference is in the numerator, can we write that as 3 over 4 plus 5 over 4? Well, this is what? 8 over 4, which is 2. Is that the same as this? 3/4 and 5/4. That's the way that works. So 3/4 and 5/4 is 8/4 if we add it up, because they already have a common denominator. So if you have a sum and difference in the numerator, you can split that up as much as you need to over whatever you have in the denominator. In this case, it's a single term denominator. But if you have a sum or difference in the denominator, can't do that. We're stuck. So back to the problem itself. Here's what I was hoping would happen, is that you would say, oh, the degree of the numerator is larger. This line right here means I need to divide if in fact the degree of the numerator is larger than the denominator. So this becomes r squared divided by r plus 4. So that polynomial type division. How many times will r go into r squared? R. So r times r is r squared. We knew that was going to be the case. And r times 4 is 4r. What do you do with this stuff that you bring down? Subtract. So r squared minus r squared, that was the intent, to drop that out. 0 minus 4r is minus 4r. Are we done with the division, or do we keep going? Keep going, because we've got a linear factor and a linear term right here, so we can keep going. R into negative 4r. Negative 4 times r, negative 4 times 4, and again we subtract what we bring down. So the r's drop out. 0 minus a negative 16 is plus 16. So what do we do now? We're done with the division. Where's the 16 go? Over. So the original problem was to integrate that with respect to r. So we've now done the division, and we found out that it's equivalent to this. So instead, what's the integral of r with respect to r? R squared over 2. What's the integral of minus 4 with respect to r? And this is a natural log. 16 natural log r plus 4. Now, this was a definite integral. So the rest of the problem then is to evaluate it from 2 to 5. Question? Yes?
You
Nicole.
said in class that
Yeah.
you weren't going to give
I
us
was gonna
any
say
long
that,
division
too.
problems like that.
Oh, not like the one we did. That was
I
hideous.
thought you meant like in
Yeah.
general,
we need
like
to
you weren't
clarify
going to
that.
put any division like
Yeah.
this
That's
on the
what I
test.
thought.
That's not what I intended to convey with that statement. I wasn't going to give you one that was as hideous as the one we did in class. This is not hideous. This is very gentle and tame for a long division problem. Okay, the bonus was a tough bonus. Nobody got any points on the bonus, and it's a substitution and then another substitution after you do that one. Now, number 6. Actually, was everybody expecting a problem like number 6? Didn't I say that you will absolutely have one of these? The long way. So if somebody didn't really know how to start that problem, I honestly, and sounds cruel, I don't have a lot of sympathy for you, because that was spelled out cleanly that was going to be a test question. So if you didn't know how to start it, either you weren't really listening, or you weren't here, or you were here but you're kind of in another zone, which applies to a couple of you in here. But that's number 6. I'm just going to ask you to look at, now I did make it a little tamer than ones we had done in class, because what was A in this problem? A was 0. So you didn't have like 1 plus 3i over n, or 7 plus 5i over n. You had 0 plus 2i over n, and that's just 2i over n. So this was a tamer version than most of the ones that we looked at in class. Now, some of you also checked with integration, which I think is a valuable thing to do, and you know what was the answer, 58 thirds? And you integrated, probably took you a minute and a half, and you evaluated, and you got 58 thirds, so you knew, you had confidence that you had done this problem correctly. 5 was a gimme. You're differentiating an integral. What is that? That's the fundamental theorem of calculus. If you either integrate the derivative or differentiate the integral, aren't you right back where you started? You should be, except the variable changes. We don't have t's anymore because we evaluated from 4 to x cubed. So wherever there's a t, we now replace it with what? So instead of t squared, it's x cubed squared. Instead of sine of t, it's sine of x cubed. And instead of derivative of t, it's derivative of x cubed. That's it. That was probably the quickest problem on the test. If you differentiate an integral, you're right back to where you started.
That's all we had to write?
Yep.
What happens to the 4?
I didn't even do it.
You didn't do it.
The 4, if you track it kind of from inside out, you integrate first, right? And then you evaluate from 4 to x cubed. So you have some x's and you have some numbers. Then what's the last thing you do? Differentiate. What happens to the numbers? They're gone, because the derivative of a number is 0. So that's why there's nothing else out here, because those things were numbers and you differentiated them and they're gone. So you could put this and this together. You didn't have to get the correct answer. Number 4. And I specifically found a problem, and I've asked this problem before on a test that I've given, and I asked it specifically on that test because you can do this problem either way. You have an odd power of sine, you have an odd power of cosine. So whichever way you chose to do the problem, it will work. So the first way is to take one of the sines send it out there to the right with the hopes that that is going to be du. That squiggly underlined stuff is going to be du. And for that to be du, so if sine is the derivative of u, what's u? More or less cosine. We can correct for SIG and stuff. So if this is going to be du, we're going to have to let u equal cosine. Derivative of u is negative sine. So we can correct for the negative. That's not an issue. But that's in cosines, but this is not. What can we do to sine squared so that we can convert it? So it's not sine squared anymore. It's something.
1 minus cosine.
Okay, good. So we know that sine squared is 1 minus cosine squared. So we don't have sine squared, we have sine squared squared. So this becomes 1 minus cosine squared. And it doesn't matter how ugly that first part becomes. We've got to make sure that that first part is what? All in terms of cosine. And then this becomes derivative of cosine. So we would square that. First term squared. The middle term is twice their product. The last term is the last term squared. This is probably the longer of the two methods. But at least it's workable. Distribute the cosine cube to each of those. Now you have a function of cosine, and out to the right you have the derivative of cosine. The other way, let's at least set that up, is quicker.
Doesn't matter when you stop this review.
Well, you don't need to do it until it kind of becomes necessary in the problem. You could take one of these out, send it out there by itself, with the intent of that being du. Well, if cosine is derivative of u, what's u? Sine. That's already sine, so we have to convert that to sine. Again, multiply that up, sine to the 5th minus sine to the 7th. So that's u to the 5th minus u to the 7th, and all that is du. So either way it worked. This was a little quicker, but the same basic premise. Okay, there is another problem in WebAssign that we can begin and at least get it to a point where you feel comfortable. This is problem 9. Now the directions say, by completing the square in the quadratic and making a trigonometric substitution, evaluate the following. All right, so let's take 3 minus 2x minus x squared and make that number squared minus variable squared, or vice versa, something that we worked with in trig substitution. I don't like the negative in front of there, so I'm going to pull a negative out in front of everything. X squared plus 2x minus 3, is that equivalent? I'm going to send the minus 3 out there by itself. What makes this right here a perfect square? X squared plus 2x plus 1. Don't you take half of that coefficient, right? Square it. So I'm going to add 1 here. What did I just do to this? I can't just add 1 to it. Actually, I didn't add 1. I added 1 inside parentheses, which is, so I really subtracted 1. What do I have to do? Have to add 1. So I'll just put a 1 out here. Now here we've got a minus a negative 3. I don't really need the negative 3 there. I've already completed the square. So minus a negative 3 is really what? Plus 3. And I'll put that 3 together with the 1, and that's now a 4. So this is equivalent to 4 minus x plus 1 squared under the radical. Now, when we have, this would be a squared, and this would be u squared. So the variable stuff is u, the number stuff is a, and we've got that under the radical. What kind of substitution did we make? Trig substitution, but which one? We did 3. We did a sine theta. We did a secant. Which one do we need here? A sine theta. Okay? So our u is really x plus 1, right? And our a squared is 4, so a is 2. So what's the